Welcome to the fourth and final video on solving the reactions for indeterminate torsion bars. In this video, we'll go back and double check our work to make sure that both bars AC and BC rotate the same amount. We'll also check to see the maximum shear stress induced in bars AC and BC. And talk about how those need to be equal to each other because the outer diameters are the same and the amount they need to be rotating is the same. Now that we've got the torques recorded from the previous video, now let's check to make sure that our rotations are the same for either of them. So let's start with the twist from A to C, and we said before that that would be equal to the length over which it's been twisting times the torque divided by the polar moment and also the shear modulus. And that's going to be, for us, 125 millimeters times, oh, nope, not for this one. For A to C, it's going to be 68.2 kilonewton millimeters, and then that's going to be divided by the solid value for the polar moment, which is going to be 15,708 millimeters to the fourth, and also divided by G, our shear modulus. And all that is going to end up being 0.5423 kilonewtons per millimeter squared, and the shear modulus, because we never determined what the shear modulus was. However, when we look at this, we can see that the units, kilonewtons per millimeter squared, are going to be the same units that we're going to have for our shear modulus. So, if we had our shear modulus punched in here, they would all cancel out. We would have no units, which is to say that we would have radians as our unit. Let's check to make sure this is the same. So from C to B, we're going to have, well, it is the same length, but it's a different one, right? The first one was this 125 millimeters, this one is this 125 millimeters, so. And that one's going to be times 51.8 kilonewton millimeters. We'll just divide that by the polar moment of inertia for the smaller, or the smaller one, which is to say for the hollow section, and that's going to be 11,936.5 millimeters to the fourth, and again this would be divided by the shear modulus, which we've not determined what that is. So that's going to give us 0.5423. I said 23. There we go. Which is in fact the same value that we got before. Kilonewton millimeters squared, and that's still divided by the shear modulus. So these are the same values, so it is in fact going to twist the same amount. Now, so we can now also determine the maximum shear stress. So let's do that. The shear stress, we can use our elastic torsion equations that we got from the notes on Wednesday, and say that the max shear stress due to torsion is going to be equal to the torque applied times the outer radius divided by the polar moment. And so for A to C, that value is going to be 68.2 kilonewton millimeters times our outer radius, which is 10 millimeters, and we'll divide that by the larger, the polar moment for the solid bar, which is 15,708 millimeters to the fourth. And that's going to be, well, it's going to be 10/125ths of this right here. So right away we could say that we're definitely going to get the same thing for both portions, right? But we're going to get 0.0434 kilonewtons per square millimeter. This is for A to C, and then our shear stress from C to B will be 51.8 kilonewton millimeters. Still 10 millimeters as our outer radius, although we have an inner radius this time. We didn't before. We're not too worried about that. And we'll divide that by our polar moment, which is 11,936.5 millimeters to the fourth. And we're going to get for that 0.0434 kilonewtons per square millimeter, which are the same. And that's going to necessarily be true because they have the same radius. And if they have the same radius, then they're going to have the same rotation at point C. And since they have uniform rotation across, they have the same length here, they're going to have the same, and then they've got the same strain. They've got the same deflection. If they've got the same deflection and the same length, they're going to have the same strain. If they got the same strain and the same radius, they're going to have the same stress, because remember, the strain is directly related to how far we are away from the center, and also from how far away we are from, how much it's rotating. All right, so that is the end of this example. Have a safe weekend, and prepare for the exam next week.